then screen share. So yeah, I'm not going to be able to answer any questions if you guys send it through the chat. Um, so if you have a question, shout it out. All right. Module 4. Module 4 deals with equilibrium. So yeah, I'm gonna go through like a brief rundown of the concepts. You guys can look at the concept list sheet that I gave as well, because I believe that will definitely help you out. So yeah, this is just like a basic definition. Um, there are two states or conditions at equilibrium. One is that the concentration of products and reactants are constant, and two, the rate of forward reaction. Let me write that better. Forward reaction is equal to the rate of the reverse reaction. Um, reaction. Okay. So those are the two conditions that happen at equilibrium. So when a question says like something is being initially like added, that's not equilibrium. So like at equilibrium, you're gonna see the products and reactants are constant, and the rate of the forward reaction is equal to the rate of reverse reaction. And so you see this in this chart. If you look at the chart, you see that the products and reactants remain constant. And the only way for those things to remain constant is if the rates of the forward and reverse are equal. And that's what we see. So on your exam, you could literally just draw out like something like this and you'll understand it, right? And it's like, this is like one of them and then this is the other one, right? So if you know that the products and reactants are constant, then the other one has to be that they're equal, if you think like that as well. Okay? All right, so equilibrium constants, you need to know how to write out the expression, right? I think that's pretty self-explanatory. Products over reactants, and then you put any exponents, right? Um, yeah, I don't really need to go through any of the sample problems. One thing that's important is to understand what K represents. K is the equilibrium constant. And if K is greater than 1, that means there's so much more products than reactants. We learned this in module 8 and how if K is greater than 1, you're like indicating a spontaneous reaction, so a negative delta G. And this is why. There's just so much product that the forward reaction is so much more favorable than the reverse. And likewise, if you have K is less than 1, that shows that there's more reactants than products. Um, and it all goes back to like, I guess like the fact that it's products over reactants, right? If you understand that this fraction is the way it is, like if like the reactants were greater, then it's going to be less than 1. If the products are greater, it's going to be greater than 1. K differs with temperature. That's something you just need to know. It's important for like acid bases as well, because KW, but yeah. And then reaction quotient. Reaction quotient is basically the same thing as K, except now you have the initial things, right? You have the initial concentrations, and this is where the ice tables come in. And so this is a very important concept. I'm gonna guarantee you're gonna get a question about Q and T, K. But basically you have to compare Q and K, right? So Q is greater than K. Um, sorry, Q is greater than K. You're gonna favor there's more products than reactants. And so you're gonna favor the reverse reaction. Okay. If Q is less than K, there's more reactants, and you're gonna favor the forward reaction. You could think about it a little bit like Le Chatelier's principles. Um, yeah, like we said, like if K is less than 1, right? We know that there's more reactants than products, like just naturally. But if Q is less than K, that means that there like initially is less reactants than products or reactants than the equilibrium state. Or sorry, if Q is less than K, that means there's more reactants than the equilibrium state. Either way, if you just memorize this as well, you could get away with like getting the question right as well. But these are the two concepts there. And then here's just like a little brief concept, right? Homogeneous, equilibrium, heterogeneous, right? They might ask you that, and it's pretty self-explanatory. And then you have K and KP. Again, this is not going to be as much of a conceptual question as it more like mathematical. So you might be asked to like figure this out. Remember, delta N is moles of gas. RT is the gas constant, and then Kelvin, and then K is the equilibrium constant, or it would be Kc, which is the concentration, right? The original K. I believe this formula is given on your reference table, so you can use that. So yeah, like this is like a standard question you probably would get if you had KP on your exam like that. You wouldn't be really asked like a conceptual kind of question with this. But again, don't take my word for it because I never know with Professor Yusuf. He could do anything really. Um, and then after that, we have coupled equilibria. So coupled equilibria, right? All you have to do, it's similar to Hass's law, where we have to combine these things, but instead of like multiplying or dividing things by thing, like dividing the instead of multiplying or dividing the k values, we're gonna put exponents to these things. So if you want to flip a reaction, we're gonna put like a negative exponent, right, to that k value. So if I wanted to flip like N2 plus 3H2, whatever, I'd have to flip this like -1 to get the K value of the reverse reaction, which is 2NH3 yields 3H2 plus N2, right? If I want to double this, I would add like 2, right? So that would double this. So that would be something like this. And it's the same if you want to keep it the same. Like you basically, yeah, if you understand the exponents, that's like the whole idea with that. So that's a thing there. And then Le-Chatelier's principle. This is a conceptual kind of question that has like some good logic, so that makes sense. So whenever you're dealing with um, just like changes in equilibrium, so like you change concentration, you have to think about it in this way, right? So if you add products, you're going to favor the forward reaction. Remove products, you're going to favor the reverse reaction. It's all about like trying to maintain the equilibrium. And so if you like increase one thing or decrease another thing, you're going to have to basically equilibrium, like you're going to have to get back to that state of equilibrium. Add a product, you're going to favor the reverse reaction. Remove the product, you're going to favor the forward reaction. With pressure, um, an increase in pressure will favor the side with the least amount of moles. Amount of gas moles. So, yeah, adding an inert gas does nothing because it doesn't affect the pressures. Um, but if you increase pressure here in this case, you're going to favor the forward reaction because there's 2 gas moles on the right and there's 3 gas moles on the left. If you decrease pressure, you do the opposite. So you're going to favor the side with the greatest number of gas moles. And then likewise with volume, if you increase volume, it's the opposite of pressure. So if you increase volume, you're going to favor the side with the greatest number of gas moles. And if you decrease volume, you're going to favor the side with the least amount of gas moles. So if you know pressure and like the relationship between pressure and Le-Chatelier's principles, you should also be able to figure out the volume one as well without fully memorizing it. Like you have to understand it. Changes in temperature, right? So now you have to deal with delta H. They could, instead of giving you delta H, they could say that this reaction is exothermic or this reaction is endothermic. And I believe we talked about this last semester a bit, but exothermic, you release energy, endothermic, you absorb energy. So in this case, delta H is negative, so that means you're increasing or you're releasing energy in the products. So I'd like to think of it as if like the energy is like a product in this case. And so if you increase temperature, you're going to favor the side with the you're going to favor the reverse reaction because you have temperature in the product. If you decrease temperature, you're going to favor the forward reaction because you have temperature as the or you have heat as a product. So if it was endothermic, you would also have to consider it like it's a reactant and do that accordingly. So yeah, and then finally you have the ice tables, and the ice tables, like we've been talking about, it's not such a problematic thing, right? Um, First, what you need to do if you aren't able to fully like understand what you have initially, you have to figure out what Q is, and you have to compare it So like, let me write this down. First, find Q and compare K with Q. Okay. And then that will dictate the ice table. So make ice table depending on that. And then you solve using the calculator. That's like a pretty general like rundown of how to do ice charts, right? So like for this practice problem, you find out what Q is and see which reaction, like where it's going to shift. Um, and once you figure out where it's going to shift, you're going to be able to determine which side's going to have plus X or which side's going to have minus X. And then you can figure out the equilibrium concentrations in terms of X. And you can solve for X using the graphing calculator that we've been talking about in class. So, does anyone have any questions about Module 4? I kind of went through it. It sounds like I went through it pretty fast, but it really isn't like a super deep topic, I'd say, or module. But yeah, does anyone have any questions regarding this? Remember, I can't read the chat. Is my mic muted, chat? Hello? Do you guys hear me? You guys there? Have I been?
We're there.
Okay. Okay. All right. Sounds good. Okay. Um, yeah, okay. I'm gonna just move on then. If you guys don't have any questions, we'll move on. All right, acid bases. So part one deals with the general idea of acid bases. Part two will deal with buffers and titrations. Remember, I also have a video of me going through a lot of the math questions with this. And I try my best to go through some of the concepts in those videos, but if you can't like understand it, like I'm gonna go through some of these concepts here a little bit. So we got the Bronsted-Lary acid-base definition. So you want to make sure you understand the definitions between Arrhenius and Bronsted-Lary. Um, yeah, the idea that I think about is that the Bronsted-Lary definition and the Lewis acid-base definition kind of describe like what is the acid base doing within a reaction. And so Bronsted-Lary acid-base definition is very similar to Arrhenius. Um, it's just that instead of it being a base producing hydroxide, it's a base accepting a proton. Acid and the acid definition of Bronsted-Lary acid is similar to Arrhenius, but just make sure you know the definitions. Conjugate acid base pairs, probably one of the most important concepts for a lot of these conceptual questions. And it's this idea that like you can figure out a conjugate acid base pair from an acid base reaction. So the difference between a like a conjugate like acid base pair is one hydrogen. So you see how water here gains a hydrogen. This would be considered the base. And when you say conjugate acid base pair, remember conjugate acid bases are just like pronouns, right? So like in this case, right, this is acting as the acid and this is acting as the base. And then this would be the conjugate acid and conjugate base. But if I flip the reaction, right? So instead of it being like this, it would be like this, right? And then the three like that, going like this and making, I'm just flipping the reaction. And you could just say that this is now acting as a base and this is acting as the acid. And then this would be the conjugate base and conjugate acid. Like I'm saying that the conjugate acid bases, like saying something is a conjugate acid is just like a pronoun, right? For the context that we're talking about. But big idea, just know that conjugate acid base pairs are different by one hydrogen. That's like the big idea. Amphoteric are substances that can that can be both acids and bases. So water is a good example of that, but another example could be like HSO4. HSO4 can go and become SO4 minus 2, and also become H2SO4, right? So this molecule can act as an amphoteric. So you want to be just familiar with that idea. Polyprotic acids, like the intermediates in a polyprotic acid, generally can also act as amphoteric. So it's good to understand that. KW. So you want to make sure you guys remember that 25 degrees Celsius is at 25 degrees Celsius, this is the KW. I know there was one question on the exam where they gave you KWs at different temperatures, and they asked you to figure out the pH of um like at like a water solution at like 40 degrees Celsius or something like that. And so big idea, right? KW always will equal hydronium times hydroxide concentrations. That's a big idea. This is true all the time, right? What isn't true all the time is these concentrations equaling 1.0 times 10 to the negative 14, right? That isn't true all the time. So that's because this is temperature dependent, right? But this formula is always applicable. So that's why it's really important. And then yeah, pH and pOH, right? So negative log of H plus is pH, and then negative log of pOH is OH. And yeah, with it being at 25 degrees Celsius, you can get a formula of 14 equals pH plus pOH. All right. If it isn't at um like at any temperature, instead of it being 14 equaling pH plus pOH, you do pKW equals pH plus pOH. If you are prone to making mistakes or not really recognizing like the temperature difference or whatever, always just do the general formula. pKW equals pH plus pOH. Don't like, if you can't recognize like the pattern, just like go back a bit and just stick to this formula. All right, so yeah, here's a question you guys could do possibly. And yeah, like whenever you find a pH of a strong acid, you want to make sure you're familiar with the strong acids and strong bases. You can do negative log of this whole thing, because that's the equal to the hydronium concentration, and likewise, this is equal to the hydroxide concentration. So you can do 14 minus the negative log of hydroxide, which is the strong base in this case, which would give you the pH. Okie dokie. So this is a pretty important concepts, right? So strong acids. The idea is that the equilibrium is gonna like when it says it's far to the right, that means that the K value is greater than 1, right? If the K value is less than 1, it's gonna be far to the left. So there's more reactants and products. And so this is a good strong idea, or this is a good list of all the acids you need to like commit to memory to some extent, right? These are strong acids. I know on the exam there's a strong acid for HBr. So make sure you just commit these things to memory. And these are also strong acids. So keep these things in memory. And these are also strong bases. Most of these strong bases are pretty self-explanatory in that it's a salt.
Can I ask a question?
Yeah, what's up?
Before when you were talking about strong acids and strong bases, um, you said something about like 14 minus the negative log something, but then how do you know that you can use 14 for that? Because it didn't say at 25.
Yeah, if
So
it doesn't say temperature, you can use 14 minus the negative log of OH.
if it
If
doesn't
it
say temperature,
if it doesn't say any sort of temperature, you can assume that. But if it does specify a temperature, you can do do pKW.
then how do you just know what pKw is if you also don't know the concentration?
They would have to tell you what KW is, and
Oh,
yeah, like they would tell you the temperature and they would tell you the KW. Or if it's like a trick question, you would answer cannot be determined with the following information.
okay. Thank you.
Yeah, no problem. So yeah, this is a good list of strong acids and strong bases. And then this is a good list of strong or weak acids. Um, One thing I would also add to this list is ClO2. That's also a weak acid. Um, and it's like you could tell that from here. This is where it's from. Um, yeah, that's pretty much most of the weak acids they would expect you to know. This formula here is the weak acid dissociation, right? And that's where you get Ka values, right? So Ka is equal to hydronium times the anion over the Ha. Percent dissociation. The idea with this is that the hydronium concentration here is at equilibrium. and this is at the initial concentration of HA. So you can do a lot of problem solving with this, and that's what happens with this problem here. You can use this to figure out the ice chart here. Okay, so I'm not gonna go over a lot of these math problems just because I went over it in my video, so you guys could watch that video. Because I'm gonna focus more on the concepts, right? So here is a really important concept. Okay, I've been yelling it, screaming at the top of my mouth, at the top of a mountain for this, but um, the stronger the acid, the weaker the conjugate base. Okay, the weaker the acid, the stronger conjugate base. Okay, so it's the same thing with bases, right? The stronger the base, the weaker the acid. The stronger the conjugate, or sorry, the weaker the base, the stronger the conjugate acid, right? So this is kind of what you see here, right? So hydronium is a very strong acid. This makes water a very weak base. But then over here, um, like water is a very weak acid, and then hydroxide is a very strong base. So that's like a little like showcase. You're not going to need to memorize these, but just understand this trend. He could give you the Ka values in a chart and ask you to like rank the base or acid strength, which is what he does here. So keep that in mind. And then yes, you have like a lot of these ice charts that are pretty much the same kind of question, just slightly different, right? So this is with a weak acid, this is with a weak base, um, this is with another weak acid, but instead of giving you the like Ka value, they're asking you to find the Ka value with the pH. And so you want to make sure you're familiar with how to do these questions. So this is also a very good concept here. This is binary acids. And so, yeah, with binary acids are acids where the H is directly bound to one other element. Um, and so like you see something like HF, HCl, right? This is like halogens. Another example of this could be like H2O, H2S, right? H2SE, H2TE, right? These are also technically acids, right? But this would also be considered binary, technically. It's just that like it's one singular element that it's bound to, right? Another example could be like NH3, like pH3, right? Um, yeah, but these wouldn't be acids, these would be bases, but I don't think you would expect you to answer that kind of question. But the idea here is that as you go down a column with binary acids, you're increasing in strength. And that's because the bond between these two things is weakening, allowing the H to come off easier. With ternary acids, this is where the H is not directly bound to the like central atom of a polyatomic ion, right? So in this case, this is like um, Cl here, right? In this case, now you have to consider the electron density. So as electron density increases, you decrease the strength of this bond, allowing the H to come off easierly. Okay, so um, yeah, just keep these ideas in mind because there's definitely gonna be some kind of question regarding that. All right, hydrolysis of salts. So there's certain salts and bases that there's certain salts that can act as an acid or a base. And that's because it contains the conjugate acid or base of a respective weak acid or base. So what you need to know how to do is you need to know how to identify conjugate acid base pairs. And so an example could be something like ammonium. Ammonium is an example we've talked about in class quite a lot. So this would create ammonium chloride. And since chloride is a weak base of a, sorry, chloride is the conjugate base of HCl. And HCl is a super strong acid. So that makes Cl minus a super weak base. But ammonium is the conjugate acid of ammonia. And so ammonia is a weak base. So that makes ammonium a relatively stronger acid. So when you see that, this is a conjugate. When you see you have a conjugate of a weak something, that will indicate if the salt is acidic or basic. If it's a conjugate base, it's going to be basic. If it's a conjugate acid, it's going to be acidic. So that's why ammonium is going to produce H3, H3O plus and um, like ammonia, right? And another little like hint as well is that like if it's positive, it's generally going to make hydronium, and that's because of how reactions work. And if it's negative, it's generally going to make a hydroxide because you want to have the same charge on both sides, because that's how reactions work. So likewise, basic good examples like NaF, right? F is the conjugate base of HF, which is what we talked about. So NaF, it will produce Na plus F minus, and F minus is going to be the conjugate in this case. And this is going to react with water and produce hydroxide plus HF. And so you could do ice charts with these as well to figure out the pH. This is not plus. I don't know why I put a plus there. My fault. Um, yeah, yeah. Let me give you a little bit of a harder example. This could be like NaClO2, right? You would have to be familiar with that this is a weak base because or this is like a relatively strong base because HClO2 is a relatively weak acid. Like that's something he would expect you to know. Yeah. Okay. And then yeah, neutral solutions are going to be ones where it has the conjugate bases of weak acids. Sorry, conjugate base or yeah, conjugates of strong bases and acids. So like Cl is a strong conjugate of a HCl. So that's why it's gonna be neutral. That's why we can go in the ocean, you know? So yeah, keep that in mind. With this, you would have to be given the Ka values and the Kb values. If you were given the Ka values, you're going to be able to compare the Ka and Kb values respectively. But this is like a very involved question. I don't really feel like he would ask a question like this unless he gives you directly like the Ka values and the Kb values. So yeah, just keep this idea in mind. And then another thing to keep in mind is metals that have big charges, so like something like aluminum or like anything that has like a charge that's greater than 7 or 3, so like manganese plus 7, right? In water, they're going to produce these like water complexes. So like this would be like you don't even know how to draw this out or whatever, but let's just say it's like something like this. And it's going to like dissolve and act as a weak acid basically. So you're gonna create like it's just gonna create like hydronium and then like some other like product, right? I don't really know what, but it's acting like a weak acid in this case. And so the idea is that these kind of complexes, or even like if you have a salt that's like aluminum chloride, like this like ion is going to create this kind of complex and then it acts like an acidic ion. So the idea is that metals with high charges can create acidic solutions. All right, so you want to make sure you remember how to do the pH of these things, right? So you basically first write out the thing, CH3 COO, right? Dissolve it, Na plus CH3 COO minus, right? And then you determine this is a weak base of a weak, sorry, this is the conjugate base of a weak acid. And then you create the reaction first. So this is reaction with water to produce um, hydroxide plus acetic acid. Let me do CH3, COOH. And then you do ice chart accordingly. And then you use the initial amount. You can use the K, you have to use the KB, and then you can put it into the calculator and solve. Okay, so that is part 1 of module 5. Is there any questions regarding anything I just went over? Okie dokie. Now we're gonna get into some nitty gritty things. So part 2, I'm literally gonna name like this is buffers and titrations. It's like a pretty big idea with this, right? So before we talk about buffers and titrations, let's talk about polyprotic acids. All right. So this was in the video that you guys were supposed to watch. I don't know if you guys did watch it, but The idea with polyprotic acids, right? One concept is that Ka1 is greater than Ka2, which is greater than Ka3, and then so on and so forth, right? So like phosphoric acid, right? The first Ka value is going to be significantly greater than the second one. And then the second one's going to be significantly bigger than the third one. Um, and why that's important is if they ask you to find the pH of phosphoric acid, you are going to be able to just use only the Ka value of the first one to find the pH because the hydronium produced in the second and third one is so much more insignificant than the first one because of that exponent here, right? So if you go back to the idea of K values, right? Um, like the K value represents the amount of reactants and products that you have, right? And so this first one is like to the -3. So obviously there's not going to be a significant amount of hydronium from that. But in comparison to -8, -8 is like barely anything. And -13 is like practically nothing. So that's why -3 is going to be superior in that case. So in order to find the pH, you just need to use this first Ka value if they give it to you. H2SO4 is the only example of a polyprotic acid in which H2SO4 is going to dissolve and produce HSO4 plus hydronium regularly, right? This is going to happen regularly. And then the second one doesn't happen as regularly. So that's why they give you a K value because this is happening for the second guy. So that's going to create SO4 minus 2 plus hydronium. So yeah, this is like the whole idea with this. Um, so you want to make sure you understand that this is a one-to-one like thing that's happening. Like if this is like 1.75, this is going to also equal 1.75. But then here, you're going to get a Ka value of something. And so this is not going to be like even though this is 1.75, this is 1.75, you're going to add like not not 1.75. You're going to add like something in between those two values of like 1.75 and 0 because the Ka values here. So it'd be like minus x, 0 plus x, right? And then you solve for the Ka value to figure out the x, which is the hydronium concentration produced and solve. So keep that in mind. Yeah. Now we're talking about buffers. So the concepts of buffers, right? There is going to be a question regarding composition of buffers. And I don't want you guys to get this wrong. Please don't get this wrong because this is a very simple question. Buffer composition, right? You have to have a weak acid and its conjugate base, and a weak base and its conjugate acid. Okay? That's it. Okay? One or the other. You will never see any time like a strong acid and a strong base in a buffer ever. You're never going to see that unless they add it or whatever. But they're not like if they ask you which of the following could possibly be a buffer, make sure you know this concept, please. Okay. All right. This is like it's like free like points at that point, right? Um, all right. I'm not gonna sugarcoat that. Please try to get this right. Okay. And yeah, how buffers work, right? If you add like a strong acid or strong base, the buffer is going to like replenish itself basically. So when you add hydronium, you're basically this base is going to react with the acid and produce the conjugate acid, which is the thing there. And so like that's how buffers work. So you can't have something that isn't a conjugate. So remember, weak acid, conjugate base, or weak base, conjugate acid. All right. So whenever you're asked to find the pH of a buffered solution, and this is definitely going to be a question on your exam as well, when you see you have the acid, you have the conjugate base, and you have the Ka value, you do Henderson Hasselbalch. So pH equals pKa plus log of base over acid. Okay? Make sure you remember that. Okay? When you have conjugate acid, when you have base, and you have Kb or Ka, right? You need to convert to Ka and use this formula. Okay. Base always goes on the top and acid always goes on the bottom. All right. When you like see this, like this question should take like 30 seconds. Okay. Or a minute, right? But like I'm telling you, you're definitely going to see a question where it's like this. All right. It's literally going to be the same idea, just with a different Ka value, a different acid, and a different base. but it's going to say the same thing. Find the pH. Okay. I'm sorry for yelling at you guys, but I'm just saying, I'm trying to drill in your head, guys. If you guys are listening, I feel like am I talking to myself? I don't know. Okay. So yeah, keep this formula in mind. And so when you add an acid or a base, a strong acid or a strong base to a titration, that's where you have to do ICF. So you're going to, with like the idea in mind. So if we're adding NaOH to this like buffer here, right? That NaOH, it's a base, right? So bases will always react with acids, and you're gonna do like the acid base reaction. And typically when acids react with bases, you're going to produce a salt, right? Some kind of salt plus water. That's like always like the general formula for a acid base reaction. Okay, so you're gonna do ICF. You want to make sure you remember like the volume, right? So if you're adding like a specific volume of base, you have to add that to the overall like volume when you find the final moles. Remember, initial is also moles. Change is basically because it's a strong like when you're adding a strong acid or base to a thing, it's always going to go forward, right? It's not equilibrium, right? Strong acids and bases will cause the reaction to go like the acid base reaction to go forward because they're very strong. Um, so yeah, like the reactants is going to have the minus and the products are obviously going to have the plus. Um, yeah. And then after you find the concentrations, if there's still the conjugate acid base left, like if there's still some amount of acid and base, you can use Henderson Hasselbalch and solve for the pH if they give you the Ka value. Okay, so to summarize what I just talked about, you do ICF followed by Henderson Hasselbalch. Okay. Okay, dokie. I believe there was a question on your last exam that was similar to this. So if you could identify this kind of question and like if you know that this is the like way you have to do it, then like you shouldn't have such a problem with this kind of question. And if you do have a problem, just try to practice these kind of questions. Like I know you guys did these sample questions in class and whatever, but I'm telling you, there's only so many questions you could ask. So yeah, like these are all the math kind of questions. So buffer capacity just deals with the amount of H plus and hydroxide that a solution can absorb. The idea with buffer capacity, and this was also a question on your exam, is that you want to have the maximum amount of acid and conjugate base. So let's say instead, like I had like 2 molars of acetic acid and 2 molars of acetate, right? Right, or sodium acetate, right? And I was comparing that with like 0.1 molar of acetic acid and zero point 0.1 molar of um, sodium acetate. Which one has the higher buffering capacity? Obviously, the one with the greatest number of concentration. Okay, that's all this kind of question is asking. Okie dokie. So, um, yeah. So this is also another thing that's talking about this, right? Optimal buffering occurs when both of these equal one another. So when they say like the best effective buffer, you're gonna want a concentration that equals one another and is the greatest. He's not gonna give you like a weird example or anything. Like it's gonna be pretty self-explanatory. Okay. So now this is again a question, but instead of it being adding base, now you're adding acid. So this is like again a similar kind of question that what we talked about last time, which again is just ICF followed by Henderson, right? So just try your best to remember that. Now acid-base titrations. So the concepts here is um yeah, so the titrant is the thing that's being added. So that's the thing that's in the burette. So like if you're titrating like acetic acid with like if you're like let's say hypothetically, let's talk about the graphs first, right? So we have a weak acid titration graph, right? You want to make sure you remember the graphs, right? So in a weak acid titration, the pH at the equivalence point, so this is the equivalence point, right? This is gonna have a pH that's greater than 7. So let's say that this pH here is gonna be like 8. And that's because at the equivalence point, you're gonna have a conjugate base of a weak acid at the equivalence point. So this goes back to the idea of hydrolysis of salts. So going back to this point that I was trying to say here, like in the burette, right? If um like the titrant in this case would be the base, like so like sodium hydroxide, and the in the flask it's gonna be like the weak acid, so like acetic acid or something. Okay. So the titrant is the thing that's being added. Um, but yeah, this is one of the graphs you need to know. The other graph you need to know is weak bases and strong acid titration. So it's gonna be something like this, right? And here at the pH value, it's going to be a pH that's less than 7. So like let's say 6. This is the equivalence point. And the idea is at the equivalence point of a weak base strong acid titration, uh, the pH is less than 7 because at the equivalence point, you have the conjugate acid of a weak base. All right, so back to that idea of hydrolysis of salts. Okay, you want to make sure you're familiar with this graph as well. And then to two other last graphs that we're going to talk about is strong acid, strong base titrations. So this is a strong acid, strong base titration. So it's going to be like, whoop, right? And the pH here is definitely going to be 7, right? At the equivalence point. It doesn't look great with the graph, right? Over here, we're going to have a strong base, strong acid titration. And again, the pH is also 7. And that's because the conjugates at these equivalence points are conjugates of they're conjugates of super strong acids and bases. So that's why these pHs are 7. I know on the exam there was a question I gave you a bunch of concentrations of like they said like let's say you're adding like HClO4, right, with a concentration of 1.0 times 10 to the negative 4, I believe, and you added like 0.15 molar of NaOH. And they were like, what is the pH at the equivalence point? Okay, this was a question on your last exam that I saw. The idea with this is that the like concentrations here, right, are irrelevant. They're asking what the pH is at the equivalence point. So you refer back to those graphs said, and strong acid, strong base, the pH has to be 7. Has to equal 7. So that's like the idea with that. That's the concept there. So this is like a little trick question where they give you like these BS like concentrations that you don't need to use because they're asking something completely irrelevant to that. Okay? So again, this is like the idea with any sort of the titrations. These are the math questions. So with any of these questions, you're going to do ICF. So the beginning one, obviously, you do negative log of the acid. You do ICF followed by like negative log. You do ICF. This is C is at the equivalence point. But you just still do ICF to see if it's at the equivalence point. And once you know that, you know pH is equal to 7. And then again, you do ICF and then you do the negative log of the base, excess base, right? That's how you do strong acid, strong base titrations. He's probably not going to ask a question like this because he probably would want to do some other sort of titration, like weak acid, strong base titration, because I think it tests a little bit more, but I can, I'm not going to guarantee that this question wouldn't be on the exam. Um, and then, yeah, this is like the idea. This is the graphs that we talked about. And likewise here, um, yeah, this is the weak acid, strong base titration. So first things first, A, it's going to be ice, right? You have a weak acid, right? So this is the same kind of question before. B is going to be ICF, right? So you're adding a base to this. And when you add a strong base to a weak acid, you're going to produce its conjugate. And so that's why you can use Henderson-Hasselbalch afterwards. Because because KOH is the thing that runs out or like is used up, you're going to be left with weak acid and its conjugate. So that's why you can use Henderson. So B is ICF followed by Henderson. C is ICF, and because you only have the conjugate left over, you're going to do ice with the conjugate. So similar to the hydrolysis of salts. And then D it's going to be ICF. And then afterwards, you're going to have to do the negative log of the strong base. Um, and so this is very similar as well to weak base strong acid titrations as well. So if you were familiar with this, definitely check it out. If you're not familiar with this, watch my YouTube video where I go over this like a little bit more in detail. So those are math questions. These are the concepts, right? So I talked about how the pH is always greater than 7. Um, so yeah, keep that in mind. Weak base, strong acid, keep this in mind as well. Also make sure you know why as well. Like I said, the reason why there's a pH that's greater than 7 is because you have the conjugate base of a weak acid at the equivalence point. And over here, it's because you have the conjugate acid of a weak base. Um, what's it called? Yeah, so this is like the general idea of the shape of a weak acid titration curve. One thing you want to make sure is at the half equivalence point, the pH is equal to pKa, right? So you see how each of these correspond to a specific Ka value? Like if you see here, this is at the half point of the equivalence point. So in between the start and the equivalence point, this is equal to, like if you do pKa, that's equal to 2, which is what's here, right? And that's because you have equivalent amounts of HA and A minus. You don't need to know this that much in detail, but just understand like pH is equal to pKa at the half equivalence point. I don't really think he would ask a question like that, but you never know. And then finally, you want to make sure you understand how acid-base indicators work. The general idea is that you want these acid-base indicators to be relatively like within the range of the equivalence point. Um, so yeah. So yeah, you want to have it be plus or minus the general range. So like phenolphthalein, the Ka value is -8.
Can I ask a quick question?
Yeah, what's up?
On the thing from before, or wait, you just said that um pH is equal to pKa at the half
Yeah,
equivalence point. Is that for
yeah.
both weak acid strong base titrations and weak base strong acid titrations?
Yes.
Okay, thank you.
Yes. But remember, with weak base, strong acid titrations, you might be given Kb. So you have to convert to Ka and solve. But yeah, good question. But yeah, the general idea with pH indicators is they have to be plus or minus the range of the equivalence point. So that's what it says here. So yeah, on the exam, they would give you the questions regarding like they give you the information regarding the Ka values of the of the indicators. And generally like indicators are like weak acids or weak bases. Um, but yeah. And that's module 5. Any questions in general regarding this? Okie dokie. Alrighty. Let's move on to module 6. So precipitation dissolution, right? Um, so with this idea, like saturated solutions, we talked about this last SI session, but it's just basically the maximum salt amount of solutes within the solvent. Um, yeah, and so KSP is again the same thing with equilibrium concentration, but it deals with salt specifically, insoluble salts. So SP is salt product. And so it's basically describing the amount of ions that are actually dissolved within an insoluble salt. So this is like a whole list of KSP values. You don't need to memorize this or know this, but it's important that you are able to, I guess, recognize this and try to figure out some certain things. So you can do an ice chart with this kind of question. You want to make sure you're familiar with these polyatomics. So chromate, right, is CrO4 -2, I believe. Yeah, it's -2. So you want to make sure you're familiar with that. Phosphate, right, PO4 -3, right? Sulfate -2. Chlorates as well, you could be familiar with. Chlorates are pretty soluble though. You just want to be familiar with a decent amount of these ions. Permanganate is an example as well. MnO4 minus, I believe that's how it is. Yeah, because Mn is +7. Okay. So yeah, just like being familiar with some of these polyatomics. And yeah, with this kind of question, you would do the ice charts, right? So you create this, right? This is evolving, forming Pb +2 plus CrO4 -2. And then 0, 0 plus x, consider the coefficients and the xx, and that equals the K value. So products over reactants, there's no reactants, so just KSP equaling the products. So one thing that's really important as well is to consider, yeah, the coefficients. So you just want to make sure you're aware that, so like barium phosphate, barium has a +2 charge and then phosphate has a -3. So that's the salt. And so when it dissolves, it's going to produce Ba +2 plus PO4 -3. So this is going to have a chart like a 2 and this is going to have a 3. So 0, 0, what's it called? Well, actually, you don't need to do an ice chart because it's telling you this concentration already. But the idea here is that if this has a concentration of 8.90 times 10 to the -9, this is going to be like times 3, and this is going to be times 2 of that. Because if this is the concentration of this is going to be the concentration of barium, like this times 3, basically. Because for every 1 mole of barium phosphate, you have 3 moles of barium. So it's the idea of like mole ratio. This is a core concept because the question is not that bad when you understand the concept. But when you have salts that have the same number of ions, you can relate their solubility. So this is a good example where they have the same number of ions. And so now we can rank these KSP values. So like which of the following salts is the strongest, is the um is the most soluble. So in this case, it would be manganese sulfide or manganese 2 sulfide. Another example would be like something like you could do NaCl, right? That's the same number of ions. You can compare the KSP of that. Um, like AgNO3, right? Like you could, it's just the only thing is like it has the same number of ions. If it has a different number of ions, you're gonna have to solve the X value using the ice charts. Um, yeah, I believe I had a question like that on my previous exam where you just had to solve the ice charts and figure out the X values. Um, and then once you do that, you're able to compare the solubilities. So again, this is similar to the Lais-Chantellier principle that we talked about before, but if Q is greater than K, right, that means there's more products than reactants. That means the reverse reactions favored and precipitation will occur. If Q is less than K, um, less than or equal to K, that means that there's technically more reactants than products. Um, but yeah, obviously there's no reactants in KSP. So like the idea is that no precipitation will occur. And so, yeah, you want to be given the KSP value for this kind of thing. And then common ion effect is very similar to the Le-Chatelier's principle. Um, so this idea is that if you add a common ion or some kind of ion that will affect the reaction, that's also going to cause the reaction to shift one way or the other. So like an example is like, it's like this is like Mg hydroxide, right? If I add Mg um, these are the ions of Mg hydroxide. Okay. So let's say I add sodium hydroxide, right? That's a common ion, and that's going to shift the reaction to the left because you're adding this. If this was like at equilibrium, I added sodium hydroxide, there's going to be more precipitation of magnesium hydroxide. And let's say instead of adding that, let's say I add HCl. You're going to decrease the hydroxide concentration in this case because you're adding a common ion, or you're adding an ion that's going to react with hydroxide and remove hydroxide from the equilibrium. So the reaction is going to shift to the right. Okay. Similarly, let's say you have a reaction that deals with like a salt, like ammonium chloride. And this is like aqueous. And then let's say it's like reacting with A, producing like B plus C, right? I don't know. C minus 2, okay? Let's say I'm adding NaCl, right? Even though I'm adding NaCl, this is still a common ion of ammonium chloride. And so this is going to still shift the reaction to the right a little bit because chloride, our ammonium chloride is still just ammonium plus Cl minus in aqueous. So that's another application of a common ion. Okay, so make sure you understand that. And then Lewis acid and bases. So this is a little bit of a different concept. So we'll make sure you know these definitions and you're able to distinguish and identify molecules like that. Generally speaking, metals are going to be Lewis acids and anything else is going to be Lewis bases. So like if you have a complex that's like cobalt and like water, like cobalt is clearly going to be like the Lewis acid and then water is going to be the Lewis base. This is a good definition or summary of all the definitions. And yeah, coordinate covalent bonds are basically when the Lewis base is providing all the electrons for that. So an example like this is like water reacting with hydrogen or H plus, right? H plus has nothing. And so water is going to like add all the lone pair there, and it's producing at the end um like H plus like this. So like all these electrons just came from water. Um, and so that's the idea with coordinate covalent bonds. So like most ligands are coordinate covalent bonds, or most like bonds between ligands and Lewis acids are coordinate covalent bonds. And so yeah, you want to make sure you're able to identify what a ligand is. A ligand is just a unique molecule that is attached to a covalent bond. So like in this case, right here, the ligand in this case would be these two molecules. So there's two ligands in this case. Now, if the ligand was attached like this is the example here, you're going to only have one ligand. But if it's attached uniquely to the Lewis acid and it doesn't attach to each other, then yeah, those are two ligands. So you want to make sure you're able to identify the ligands there. Um, and yeah, these coordination complexes, they can have a KF value. So if I have like, let's say, I don't know, like AG, right? I think this was in class NH3 2 plus, right? This will produce AG plus NH3 2, right? And this is gonna have an equilibrium. And this is the KD in this case. The KF would be AG plus 2 NH3, producing the thing here. Right, and this is a KF. So there's some questions regarding this with ice tables and stuff like that. Yeah, so that's pretty much all the module stuff. Does anyone have any questions about anything? Because if not, we'll just get into some practice problems. Alrighty, I was yapping, so now I'm going to do some practice with y'all and stop yapping as much. So let's go to the worksheets. Yeah, so let's go over some of this mock exam. Let me just erase some of these answers. Okay. So, yeah, my strong advice, like if you guys are, if you have done all the sample problems and you're comfortable and you understand the concepts, my best course of advice would be to do the practice problems from your exams, your last exam. Try to redo some of those questions maybe, or even do the questions from my practice exam, which is last year's exam. Um, so yeah, like I guess we could do questions 1 to um, 4 for now. And I'll give you guys like 4 or 5 minutes to do this. So at 4:41, I'll be back. If you guys have any questions, just shout out.
Hello.
Yeah.
Um, do we have to know the Arrhenius equation?
Oh yeah. The Arrhenius equation that was in module three,
Before,
right?
I think. Oh, wait. Or maybe that was old. I just remember having this question.
Yeah, it's in module three. I don't think you need to. If you did need to know it, all it would be is just like you plugging in values and solving. Um, yeah, like I don't really see him asking a question like that because I think that would be a little unfair for him to ask a question like that.
Is it on the
Uh,
reference table?
what's that?
Is it on the reference table?
I believe it's on the reference table. So like you don't need to memorize the formula, but you just need to just like be able to plug it in and solve for it.
Okay, thank you.
Yeah, no problem. Also, wait, has he posted the practice exam yet for the final? Do you guys know if he has or not?
I think he has.
Ooh, let me check that out. I need to check that out because I have even more resources for you guys if he has posted it. Let's
Oh,
see.
wait.
Where is my phone? I don't know where my phone is. Oh no.
He didn't post it.
He didn't post it? Um,
Yeah.
er, um, that's annoying. Okay. Well, I will give you guys the practice exam that I had from last year, or I like from my year, he gave me a practice exam. Um, and then I will give you guys that and give you guys the answer key. And there's a video I also have of me going over that test where I like go over the test, like share how I think, you know, talk about the concepts regarding each of the questions that are asked. Um, so I'll post that today or tomorrow or something like that for you guys to study and stuff. All right, I'm gonna go over these four questions. Or how about we all do this kind of together, right? So yeah, what is the answer choice for what's the answer for number one? Do you guys know? Don't be shy. You don't know what number one is? Don't say. I did not hear the answer. Okay, I'm just gonna say, all right. So the answer choice here would be A. The concept is ternary acids, right? So if you guys aren't good with, oh wow, I just switched colors. If you guys aren't good with the like concepts, whenever you're writing any question or like doing any sort of practice problem, write out the concept or the idea. That's why I gave you the guys the concept list. Because it'll help you like kind of compartmentalize what you need to know. Because you might think like everything's like all over the place, but it's only so much. That's what like my idea is, right? So number two, right? There's a question that was very similar to this question on your exam. I think it literally had 0.25 molar too. Oh brother. Okay. Anyways, okay, I was crashing out there. So the answer choice would be E here, and the concept here is H2SO4, like um just like H2SO4. This is the only exception you really need to know. All right, three, strong base, um, like finding the strong base, the pH of a strong base, right? This is ionic compound, so the only thing here is that there's two hydroxides, so you have to do 0.7 molar, which is equal to the hydroxide concentration. So negative log of this times 14, or 14 minus the negative log of this, and that'll give you the pH there. I believe the answer choice would be C or D. I don't really remember. Let me calculate that quickly. He, I know you guys might be thinking to yourself, like, this test wasn't that hard, but this test was last year's exam. And I remember last year, everyone was like, that was really hard. So it's really just a matter of like hindsight bias that we all have. Um, so don't disregard this kind of practice. Like, I know that you might think like, oh yeah, like I already did this. It's not that helpful, but it actually is pretty helpful if you just have an open mind to it. Um, okay, the answer is D, right? All right, four. Okay, which of the following solutions can be combined to produce a buffer? Okay, so remember what I said? Um, weak acid and its conjugate base, right? So this is strong, this is wrong, and this is wrong. So the answer choice is D. So composition of buffer, right, is the concept there. Okay, so yeah, I'll give you guys some time. We'll do the next, let's do the next 12 questions, and I'm gonna give you guys like, or sorry, like let's do from 5 to 12. And I'll give you guys approximately like 5 to 8 minutes to do this. So you guys got this. Try it out. So 4:49, we'll go over it. Did Professor Yusuf say he's going to give a practice exam?
Yeah.
Okay. If he doesn't give it by tomorrow, one of you guys should email him just to get him on that, because there's no reason why he shouldn't have he should post now. It's just like the practice exams that he gives are like previous exams basically. So yeah. Okie dokie. So with this question, 5, right? We see a bunch of KSPs and they're asking to rank it in like an order of decreasing solubility or increasing solubility. What am I saying? The concept here is comparing solubilities of salts with like the same number of ions, right? So this is literally straight from like the slide, just slightly different, right? And now you can rank them. So increasing solubility. So this would have this lowest solubility. So this is 1, followed by 2, 3, 4, right? So let's look for iron first, followed by zinc. So C would be the answer. 6. So we have acetic acid, and what happens when you add solid potassium acetate to it? So with this kind of question, this is probably one of those questions where you're like, huh, where is this concept from? But it's very much so like you have a solution of this. This is based off like I guess Le Chatelier's principles or like common ion effect. Um and that's because like obviously you're gonna be like looking at this and be like, what? How do I do this? Right. But just go back to the basics, right? You have a solution of acetic acid and you add acetate, right? Yes, it's a buffer. And you could think of it like, oh, you're adding base, so it's gonna decrease the pH. So that's one way to think about it. But another way to think about it is like acetic acid is already in equilibrium with water to produce hydronium plus acetate, right? And so if you add acetate, you're going to shift it to the left, um, decreasing the hydronium concentration. So that's why if you decrease the hydronium concentration, the pH will increase, right? So that's the idea with that. So common ion is there. That's the thing.
Wait, can't that also be because like if isn't acetic acid like a weak acid and then um if you like potassium acetate's like that means it's like a strong conjugate base, like the acetate. So wouldn't that or maybe it doesn't have to do with that actually, never mind.
No, no, no. I mean, you're kind of like on the right page with that. Because like technically, the acetate would also react with the hydronium to some extent. Which is what we're seeing here, right? You're adding um excess like acetic acid, which does react with the hydronium, right? Um, so like you could think of it like that as well. Um, but yeah, like the bigger idea is that this reaction, right, is the reaction that's initially happening in a solution, and you're adding acetate, so that causes yeah, the pH to go to the left because you're decreasing the hydronium concentration. But yeah, good question. So, yeah, now we have to do these equilibrium questions, right? So this is A, B, C, right? You probably had something like this on your exam. I don't really remember, but all right. So adding calcium carbonate. Calcium carbonate's a solid. Um, and so that's not going to do anything. So that's going to be C, not affected, because solids don't affect equilibrium. If you're adding a system with half the volume, that's the same idea as increasing pressure. So you're going to favor the side with the least amount of gas moles. So on the left, you have 0 gas moles. On the right, you have 1. So you're going to favor the left side. So it's going to shift left. The reverse reaction is favored. All right. System is heated. This tells you it's an endothermic reaction. And so that means the heat is on the reactant side. And so if this heat is the heat is added, it's gonna shift right. Calcium bromide is added. So calcium bromide is soluble to some extent, right? And you're adding calcium, this ion here. And so because of that, it's gonna shift to the right. Okay. So when it exhales into the system, you're adding carbon dioxide, which is a product. And so that's going to shift it to the left. And so all of these questions are based off Le Chatelier's principles slash common ion. And then here is just like, what's the equilibrium expression of this, right? So this is based off the previous thing. So in this case, it's going to be carbon dioxide and Ammoni. Yeah, that would be it. Yep. Yep. Yeah, it would be C. So it's based off the reaction up here. Okie dokie. Uh, yeah, let's try to do some more questions. Let me try to get some harder questions. Let's see. Let's do let's do 14 to 16. So I'll give you guys 3 or 4 minutes to do this, and at 4:58 we'll go over it. Also, like I'll go a little bit over time just so we can go over some harder questions. And then yeah, you guys can have like any questions you have for me. Take advantage of this time, like ask me like hard questions or questions you're confused with or whatever it may be. Because I'm here for y'all. Okie dokie. I think I gave you guys the time that I said, but if not, it is what it is. You guys can watch the video. So, here's a question. They give you this unknown acid, and they ask you to figure out the conjugate acid of this specific species. And you might be like, "What? Where is this? Where is this guy?" Right? Like, I don't see this guy in the reaction that they gave. Like, it's just like, calm down, right? Go back to the basics, right? The conjugate acid of this would have an extra hydrogen, right? It's a difference of one hydrogen. So the answer choice here would be D. Okay? That's all it is, right? Which of the following statements is true regarding this equilibrium, right? So this is the kind of questions where it's like so much words, right? It's kind of scary, right? Let me write this down. CB, CA, Braun said Larry, right? That's the definition or the concept there. So let's see. The rate of appearance of HCl is equal to the rate of appearance of. That is true. That's based off kinetics to some extent, but that is true because it's 3 and 3, right? The rate of the forward reaction is equivalent to the rate of the reverse, right? So this is based off the conditions. Okay, right? So when you see this kind of question, right, you see how they're talking about the states of equilibrium? Instead of saying equal, it says equivalent. And instead of saying constant, it says do not change. It's the same thing, right? So this is all good. So the answer is D. And this is based off the conditions of equilibrium and the what's it called? And just like, yeah, like your general knowledge of like A from kinetics to some extent. But yeah. And then 16, um, you got all this. These are the equilibrium concentration. What is the equilibrium constant? So with this, you need to create the equilibrium expression. So this is going to be H4P2O7 cubed over HCl cubed over um, POCl3 times H3PO4 cubed. Okay. And so you can solve for this. I don't know why C and D are the same. It's my fault. I should have checked that. But I think you'll get the right answer. So let's plug in the values, right? So this is based off creating the equilibrium expression for K. So K and solving for K, right? Um, Again, it's not super difficult if you're able to. The only difficult thing is putting things in the calculator, really, right? So I'm doing that right now. Um, so 0.127 cubed, right, divided by, okay, everything's good. 0.0370, okay, times 0.775 cubed. Did I do that right? Let's see. Oh, that's 5, my fault. It's supposed to be 5. This is supposed to be 5. That's my bad. See, that's why you gotta check these things, right? So this is 5, 3, 3, right? So 5, and then, yeah, I got a value of A. Okay? So again, this is like equilibrium expression, right? That's the concept there. Okay, my goal with showing you guys these kind of questions is that like I want you guys to see that like these kind of questions, like you might like on the exam, you might be like, oh my goodness, like I've never seen these kind of questions. Like I've never seen pyrophosphoric acid, right? I've never seen like whatever, right? But no, you have in your own way. It's just you have to recognize the concept. And once you're able to recognize the concept, that's like the hint of how to solve for the answer. So like I'm trying to give you guys a little bit of confidence that you guys have done all these kind of questions before. 17, I'm just gonna go through quickly because this was a question that you guys had last semester. So whenever you neutralize something or it's the same thing as getting to that equivalence point. So you want the number of moles of base to equal the number of moles of acid, and specifically the hydroxide and H plus. So I'm gonna go through this quickly, right? So you got 0.01 molar HCl times 1.5 liter, right? So that's gonna equal, let's put that in the calculator, 0.01 times 1.5 is gonna equal 0.015, which is the hydronium concentration as well. And so that also has to equal the base concentration, so the hydroxide concentration. So, oh, why is it white? Okay, so 0.0150 mole of hydroxide now. And so now we have to convert this. So for every 1 mole of magnesium hydroxide, there's 2 moles of hydroxide. So 1 mole of 0. 0.25 mole, and then you can use the molarity, so 0.25 mole over liter to solve for the volume. Okay? So that's how I would solve it. I'd first find what I can find. Like, can I find the hydronium concentration first or the hydroxide concentration first? Or can I find the moles of hydronium first or the moles of hydroxide first? And once I figured that, I use that to figure out the next steps, right? And so I solve for that. 1.5 divided by 2, and then take this and divide by 0.25. And I got a value of 30 ml, right? So that's 17. Does anyone have any questions about that or anything that we just went over? Okie dokie. And I'll probably just go over 18 to 23, and then that'll be the it for it. Because you guys were talking a lot about how there's a lot of concepts and these kind of like I don't know if you guys see this practice exam has a lot of conceptual questions on this. Like you don't need to do a lot of math to solve for some of these questions. You really don't have to do, yeah, you don't have to do a significant amount. Like I know the exam had like a lot less math questions, but this also doesn't have that many math questions. But yeah, so try to do 18 to 23. I'll give you guys like 6 minutes to do that. So we'll be back at like 5:11 and then we'll go over it. Okie dokie. All right. I'm gonna go over these questions and afterwards I'm gonna probably end the call. But okay. So we're given this amino acid. We're like, what? What is going on, right? So much unnecessary information. You'll learn about aspartic acid in biochem, but you know it's triprotic. So which of the following is false? So what's not true? And so this is based off polyprotic Ka values, right? And so we see here that um A would be not true. All right. And that's just because Ka1 is greater than Ka2, right? Which is greater than Ka3, right? Okay, 19 to 22, right? We're given a bunch of acids. HNO3 doesn't give a Ka because it's a strong acid. 19, 0.25 solution of like which of the following is supposed to be the most basic? And so the weaker the acid, the stronger its conjugate base. So if this is the weakest base or acid, you're gonna have the strongest conjugate base. So that's why NaCN would be the strongest. So the thing here is strong, like acid conjugate base relationship. That's the concept. Which of the following lists correctly rank these acids from strongest to weakest? All right, so this is just simply ranking the acids using Kas. So it'd be strongest to weakest. HCN would be the last, and HNO3 would be the first. And then yeah, you want to make sure you remember HNO2 is going to be stronger than HF. So that's what I see is the answer there. Okay, so this is just ranking based off Ka values, which is the question you guys did in class. If this acid is titrated with this amount, what is the pH at the half equivalence point? So that's pH equaling pKa, right? So pKa of HClO, right, is negative log of 2.90 times 10 to the negative 8. And I believe that it's going to be, let's put this in the calculator. Calculator, negative log of 2.9 times 10 to the negative 8. And that's going to be, yeah, 7.54. So D. That's a half equivalence point of that. What is the pH of 0.275 NaNO2? This is based off, like, it's a hydrolysis of salts now. So hydrolysis of salts, it has a conjugate base of a weak acid. So you're going to be left over with like NO2 plus like H2O, right? Reacting and forming hydroxide plus HNO2, right? And you're gonna do an ice chart and you're gonna figure out the hydroxide concentration and figure out the pH. But just like off the top of your head, you can tell that A, B, and C would all be wrong because it has to be basic. So you can guess between D and E. Yeah, I don't really remember the answer choice for this one. And I don't really want to go through the trouble of doing it, but it might be E or D. Yeah, but I'm gonna move on. Pyridine, right? Dean, blah blah blah. It's a thing here, and it's asking you to identify what kind of acid and base it is, right? And so when you have these nitrogens, it's very similar to ammonia, right? So it can act like a bronzillary base and a Lewis base because it's able to accept a hydrogen and it's able to donate its lone pair and create a bond with like H plus. It's very similar to that water concept. So like the water thing that I showed you guys where it's like H, right, with H plus, right? This is going to literally yoink the H plus there. And the same thing with this. This like think about it like it's like N with one lone pair connected to like the carbon like that. So that's why D is the answer there. Okie dokie. So I went over some of these concepts, right? My goal is that you guys are able to like when you take this exam, you make sure you know all these like concepts so that there's nothing you see that's gonna surprise you. That's like my goal with this. But yeah, all right. If you guys have any questions about anything, let me know. Yeah, I'm gonna stop the recording here. So stop.